Thank you. Okay, so let me just recall what I was doing. The situation I was considering is we have M, a compact complex manifold, and there we have a lamination by Riemann surfaces with a finite number of singular points. Just for simplicity. And then we constructed in several ways. We showed that there exists a current T positive by dimension 1, 1 along the lamination, meaning that when it's defined by continuous form, it satisfies this, and which is IDD bar closed. Another way to phrase this is to say that in a flow box away from the singularities, T is represented in the following way: H alpha, V alpha, d mu alpha. V alpha are the plaques. D mu alpha is a measure on a transversal here. And H alpha are positive harmonic functions here. The existence of such guys is not limited to this context, because I can consider also an abstract lamination without singularities for simplicity, and still we have such an object. So for example, we could consider the situation Christian was dealing with this morning. There is a question that did appear several times in these lectures by other people, by Marco this morning. Sometimes there are positive closed currents. T is closed means that you replace this equation by just dt equals 0, and then you have the representation V alpha d nu alpha, meaning the positive harmonic functions are constant. Since this is a course, actually I think it's good to give a proof of some elementary fact. And I want to give you a criterion when does there exist a transverse measure or a positive closed current. Here is one. Suppose P is a parabolic Riemann surface. So you have a map onto a leaf, phi. Then I claim that there is a positive closed current. Let me call this P parabolic, because just for this lecture. Because this morning, Marco considered the Riemann surfaces which were parabolic, and in his mind, they were just covered by C. Parabolic in the sense of potential theory means this P is P parabolic if no non-constant bounded subharmonic function. A good example of parabolic surfaces is C. But you can remove from C a small set, like a polar set, 10 points, for example. Then it's hyperbolic, but it's still parabolic in this sense, okay? Because bounded subharmonic functions are constant. Then it is known and classical that this is P parabolic in this sense is equivalent to the existence, let me see, how do they call it, sigma of an tau and exhaustion function subharmonic and d bar tau is 0 out of a compact. For example, in C, the function tau would be log plus z. This is an exhaustion function. It goes to infinity at infinity, and its Laplacian is 0 out of a compact. So I want in 5 minutes to construct this current in this generality. Okay? Just to show you which type of computation you do. Then let me define sigma to be e to the tau, Vr to be log sigma over r, and key to be the max of t and 0. And I define SR to be, SR of psi to be log plus r over sigma phi star of psi. This is a current. I have to tell you how it acts on forms, on 1-1 form. You pull back this 1-1 form, then you are in P. You multiply by this function. This function is just supported when sigma is less than r. Yes, when sigma is less than r. For example, in the case of C, it would be when z is less than r. This current is certainly not closed. But as I told you, all currents are constructed by taking limits. And as Christian pointed out, the problem is to estimate the boundary in terms of the area. Show that the boundary is negligible when R is large in terms of the area. So this is key of this. Key is just log plus. It's just max of t or 0. This facilitates the computation. Then I have to estimate SR of deep C. This is not exactly the current because I have to normalize, and then it will at some point so that the mass is 1. Okay? So I will have to divide by key log r over sigma phi star omega, where omega is a positive 1-1 form on the manifold. So SR of deep C is just this. SR, DSR of theta, of a form theta, should be minus SR d theta. And this is, no, maybe I should keep this. This is key prime of VR, dVR, phi star of theta. This is what I have to estimate in comparison with this. Then you use Cauchy-Schwarz inequality, and this is key prime VR, dVR, dCVR to the power 1/2, and here key prime VR phi star theta, phi star theta, phi star theta bar, this is going to be bounded by phi star omega to the power 1/2. And then we have just to show that the following quantity goes to 0 when r goes to infinity. Divided by what I have written here, K VR phi star omega. We have to show that this goes to 0, or at least lim inf goes to 0 when r goes to infinity. So we have to work a little bit, and the main trick is just this one, dvr dcvr is d log sigma dc log sigma, and you do integration by parts. Being integration by part are very powerful tool, except you have to know where you are going. And where we want to arrive, and I'm not going to give you the details, is just to 0r dt over t b t, and here ddc log sigma. Why we want to arrive here? Because we know that ddc log sigma is compact support. So this is going to tell us that this is of order magnitude log r. Once you have that, I leave the rest as an exercise. You just put AR is this. Take derivative, and it's really a calculus exercise to get to the end of this. So you find, the contradiction is if you have this larger than C for arbitrary R, you end up by finding that 1 over AR0 minus 1 over AR is larger than log R, which is impossible. So here is the hint. But independently of the interest of the result, this is just to show you how do you construct closed currents. So far we didn't do too much. But still, what is the picture? We have a foliation. Imagine a foliation of PN, CPN. We have leaves. As abstract Riemann surface, what they are. If they are parabolic in the sense that I said, then you can construct a positive closed current, a transverse measure. If you have no parabolic leaf, then not only you can construct a DD bar closed current, but you know also that every leaf has non-trivial bounded subharmonic functions, which is interesting. So, hint for the students, this does not imply that there is a measurable function which is subharmonic on every leaf. Because life is tough with in foliation theory, there are measurability problems. So let me now go back to these currents, DD bar closed currents, and I want first to justify the name of harmonic measure and tell you some results that I consider of somehow natural. So let me just see which order I did think of. Yeah. I want to define the Laplacian. So we have leaves here, and we are in a complex manifold. And now we have a current T. I can take any one form beta and consider T wedge beta. For example, beta could be omega p, the Poincaré metric form, or omega, a smooth 1-1 form closed if you want. Or another form, I tau tau bar, but it could be quite irregular. Okay? I take a smooth function u, and I define the Laplacian of beta u by the following identity I dd bar u wedge t. U is smooth, this is well defined. So I'm using Radon-Nikodym theorem here to define this, which means that I'm assuming that T wedge omega is absolutely continuous with respect to T beta, and that's not too strong. This way I have defined a Laplacian, and it's a Laplacian with respect to metrics that can be very wild. Okay? The measure m beta, the harmonic measure, is by definition T beta. And if you consider delta beta u with respect to this harmonic measure, it is I dd bar u wedge t. By definition, it's 0 because you can put the I dd bar here, and it's 0. So this is why we consider a harmonic measure. We call that harmonic measure. Okay? But let me emphasize that beta could be quite wild. Okay, what do we want to do out of that? So I have to state a Birkhoff theorem in this setting. So I'm in the previous setting. It could be a lamination in a manifold, but it could be also an abstract lamination without singularities. So the theorem is joint work with Tien Quang Dinh, Nguyen Vietan Nguyen, and the theorem says this. For simplicity, I just take T extremal dd bar closed current. If you don't like that, you just consider m beta. Then I define m for every A. I assume that T gives full mass to hyperbolic leaves. and that T wedge omega P is finite. But I have given last time a case where this holds, an important case. It is when you have a foliation with only linearizable singularities. Okay? Then I consider M RA is phi A star of log plus R over zeta omega P. And the claim is that these converge MP almost everywhere to MP. This is exactly Birkhoff-Ergodic theorem. Let me remind you of the notations. Phi A is the universal covering map from D to some leaf, the leaf through A, and phi A of 0 is A. So A lives on the foliation. So
just to detail, you said it's exactly Birkhoff-Ergodic theorem. It's a weak version of it.
no, I'm going to express it right.
Cesaro form of Ergodic theorem.
No, this is exactly it.
I mean, Birkhoff-Ergodic theorem is taking the average as constant.
This average is here.
Yes, but this is not constant.
This is,
You have its weight.
no, but this is, another way to write this is dt over t from 0 to r, phi A of, it's Cesaro, yeah.
It is a Cesaro version of the Birkhoff-Ergodic theorem.
But Birkhoff-Ergodic theorem, you take average.
Not, but you take the average with constant coefficient from 1 to t.
You take an average dt over t. This is like in, yeah, okay.
In Birkhoff-Ergodic theorem, you take the constant average from 0 to t.
You're right. This is a version of Birkhoff. I take an average which is of Cesaro type.
But if I say that, it is because the usual Birkhoff-Ergodic theorem is much easier to prove in its Cesaro version.
Yeah.
But this is a detail.
This is a detail because this is much harder than Birkhoff-Ergodic theorem. Oh. So let's see, phi A 1 dt omega p. Okay, so what is the meaning of this? It is just that you take U in L1 MP. You take U in L1 MP, and you consider 1 over R phi A star of U omega P log plus R zeta converge to MPU. So this tells you that certain, may have to say a connection, R is log 1 plus small r 1 minus r, as we are in hyperbolic metric. Yeah, so this tells you that some averages converge toward the mean value with respect to MP.
So here the wheels can be parabolic also, but you suppose that...
Exactly. exactly. They suppose if there is a priori mass on parabolic leaves, parabolic meaning non-hyperbolic, because you have then you just take out that mass and that's it. Okay. So it's
You make the assumption extreme
yeah.
body, so there is mass, there is full mass.
Exactly. Because, but you can, there is a version where I don't assume it's ergodic. It's just that quite easy technicalities. Another way to express this is that you can express that in terms of currents. Here I'm using the Poincaré metric. But at the end, it's certainly used in the proof. But at the end, you can suppress the Poincaré metric and just express it in terms of currents. This means that you look at TAR is 1 over the mass of phi A star log plus R over zeta converge to T. This means you divide by the norm of this current. Okay? And it converges to T. So here we have an ergodic theorem, say Birkhoff type theorem. We have convergence almost everywhere here. Now, there is a case that was done before that, which is a theorem with Fornes. It says that take F foliation in P2 with only hyperbolic singularities no algebraic leaf. So this is a pretty generic situation. Then there is a unique, the important word here is unique, positive DD bar closed current of mass 1 directed by the foliation. This implies in particular that when you take any A and any R here, this implies that this current for every A, you have TAR converge to T. There is some similarity with what Christian discussed this morning. He was, it was this morning. He had a suspension, and he proved unique ergodicity for that in that case. Actually, the techniques and the technology are very, very different. But so anyway, I'm not going to discuss too much on that. And the last theorem I want to state is the following. Hopefully, I have kept the definition of d beta u here. There is a classical tool that was the tool used by the people who explored the theory of laminations from the analytic point of view, which is the heat equation that was used by Lucy Garnett and Alberto Condell and probably others. And you have leaves, you have a Riemannian structure, and you consider a Laplacian. In my case, it will be this d beta u. And then you consider the heat equation with respect to every leaf. The Laplacian here is the Laplacian along the leaf. And you are, do I put t, 0, x is a given function u0 of x. So this UTX is called STU because these guys form a summate group of contractions. Then the theorem I want to state is the following. Take du over dt minus delta beta u equals 0, and u of 0x is u0 is in L2 of m beta. By mean like this, there is a solution, there is u, tx, which is defined m beta almost everywhere. I will tell you why. So we solve the heat, maybe let me just state then, and then you have 1 over r, 0r utx dt converge to u0 m beta. This is also an ergodic theorem. I'm in the same context that I have m beta supported on a hyperbolic leaves. That's it. So let me now discuss this and then the Birkhoff type ergodic theorem there.
What's the difference with the Garnett's ergodic theorem?
I'm going to tell you. So, in Garnett's ergodic theorem, classically, what you have is the following. You have a foliation without singularities. So the leaves are of bounded geometry. Bounded geometry means that they are complete and there is a positive lower bound for the sectional curvature. Okay? Then, when you are in that situation, you have the heat equation on manifold, and the estimates depend only on the bounded geometry. Hence, you can use them to solve the heat equation simultaneously, in some sense, with estimates on leaves. And what you use is that this ST is contracting in the uniform norm. Here, even if you are in P2, the geometry is not bounded. The leaves, because of singularities.
But they are not hyperbolic. You put the hyperbolic matrix on the leaves. So it's complete.
It turns out that, but they are not bounded with respect to the ambient metric, which is what we do, and they might exist other parabolic leaves around. You are not going to have uniform estimates. So the idea is, instead of using the theory of L infinity norm for estimates, you are going to change somehow the point of view and consider that the manifold is replaced by the current T. Okay? And actually, you forget also the foliation. That becomes irrelevant. We solve the heat equation with respect to the current T. This means that I have defined the Laplacian. The only thing I need is that when I consider dt and define this, I need also that this is finite. So in some sense, and I can give examples, you solve the heat equation on an object that has no smooth structure. And you solve with respect to m beta. Here, okay, so let me maybe just now explain what is the approach. The approach is actually very elementary. It's far more elementary than the classical approach when you have foliations and without singularities, etc. It's more elementary. So, we have introduced a Laplacian, d beta, but what happens is that you don't have u d beta v, dm beta. This is not symmetric. So because of time, there is a possibility to introduce another Laplacian, which is d beta plus 1/2 gradient beta, and gradient beta u t beta is just real part of I d bar u tau bar t. Now, the theory is this. We introduce the Sobolev space with respect to the current T. This is going to be u square m beta plus I du d bar u wedge t. This is the Sobolev space with respect to the current T. And we introduce the quadratic form Q tilde uv is minus d beta u v t m beta, and EUV is Q tilde UV plus UV m beta. These are quadratic forms. What is the connection? The connection is this, is that it's obvious that EUU is larger than U square 1. Hence, there is a theorem of Lax-Milgram, a classical functional analysis, which says that for every f, for example, in L2MB, you can solve this equation. And this you interpret as U minus delta beta U is F. Now, the point is this. There is a well-known theory of maximal monotone operators. They tell you when you can solve the equation d over dt minus AU equals 0 and U0 x equals U0 given. And this requires only, in general, when you have a differential operator on a Banach space, it's not everywhere defined. It has only a domain of definition. And you have to check two hypotheses. That A is monotone. Monotone, as you imagine, just means that AUU is positive. And maximal monotones means that identity plus A is surjective. Here, it's very easy to check that. And the way to check it, the connection, A is going to be minus the Laplacian. What is the connection between the Laplacian and this space? Well, it comes from this. I dd bar u square is just 2I u dd bar u plus 2I du d bar u. And hence you have the connection that basically minus u delta beta u and beta is just I du d bar u t. That permits to check that this operator is monotone. Okay? Because I show that AU is positive. The fact that it's maximal monotone is what I used here. Consequence, there is a powerful theorem called Hill-Yoshida. It tells you can solve this equation. And that gives this. That gives this. And this is classical ergodic theorem. And you can prove also mixing in this case, which means that U, T converge to a constant in LP and almost everywhere. So that's the strongest possible ergodic theorem. So I believe even classically, this approach is much simpler than the one by by Lucy Garnett and Kandel. Besides, I emphasize that, though it's not probably very interesting for foliation people, is that you can solve that just on any current which satisfies this hypothesis. That's it. This is a Frobenius condition for the current, and this is a boundedness of mass, and that's all. To interpret the equation after that, you better have a lamination or foliation, but there is also no transverse regularity, nothing. Okay, so
Some people have tried to do some ergodic theory with non-integral bases, like contact structure.
yeah,
So they play similar games. But instead of take a random path, but instead of taking a random path in a leaf, because there is no leaf,
yeah,
take a random path tangent to the plane. You run it in the curve. So you go where you look at where it's going. They have ergodic theory.
okay, maybe, but I was not aware of that. You will tell me the reference.
They have very strong assumptions like the smooth contact structure.
No, but here you don't have anything smooth, not much. Besides a Lucy Garnett theorem, if I'm right, is in a manifold, and she requires some transverse regularity and things like that.
It's a manifold because at the time laminations were not fashionable.
Okay, that's fine. Still, you need, here, you don't use a heat kernel. You don't write a heat kernel. So now let me turn to the ergodic theorem, the Birkhoff type ergodic theorem. Let's see, how do I? So here is what I want to prove. I have MR is 1 over MR. MR is basically R, but it's the total mass. Phi A star of log plus R over zeta omega p. And this is the same thing as like 1 over MR 0R dt over t phi A star of dt omega p. And the theorem states that MAR converges to MP, which is by definition T wedge omega p. We have also conversions, so also conversions in LP, MP, for P between 1 and infinity, 1 and infinity, and also MP almost everywhere. The idea of proof is the following. So we introduce the averaging operator And this is the operator you want to show when r goes to infinity. I told you already what is the connection between capital R and little r is just that this. So we want to show that when r goes to infinity, these converge almost everywhere to what is said here, to MPU. In principle, with ergodic theorem, you first try to check what is the norm of your averaging operator. That means you have to show that BR U T omega P is UT omega P. And in Birkhoff theorem, this is trivial because it follows just from the fact that the measure is invariant. There is nothing to check. Here, it's far from being trivial, and that's a very delicate point. I'm going to try to explain to you why. Because you have to work with this universal covering map. Universal covering maps are defined up to a rotation. You can change this. This is also another universal covering map. There is no canonical way to choose them. So it is difficult to work with that. Besides, this turned out, or should be, just a Fubini theorem. But Fubini theorem is for product space. Foliations are certainly locally product, but far from being products. So you have to reduce yourself to this situation where we are almost in the product case. So there is a type of subdivision that means you take a transversal and you divide it in enough pieces so that you capture almost all the measure in the transversal, but the leaves up to time r will hit these pieces only at one point. And then with this, there is a bootstrapping argument. With this, you end up basically into proving, reducing the theorem to reducing at least this integration by part to like if this measure were just a Dirac mass on a leaf. And that's what gives you, besides you have to worry a little bit for one point, is that the phi are not injective. So you have to choose fundamental domains, do some computation, and you end up proving this relation. Now I'm going to do the easy part. So this way, people who didn't hear of this proof of Birkhoff theorem or will just get it. When you have, for simplicity, a compact space and a map or a measurable, say a compact space for simplicity, there are functions for which the ergodic theorem is obvious. U composed with F minus U. Then the averages collapse and you converge to what you expect. What is the replacement of these guys? The replacement of these guys is delta P. P is for the Poincaré metric of U. Then you get that BR UA is BR, this is U, BR delta P of V. So this is tau AR d bar of V. And I have showed you that d bar tau AR V, I have showed that this converges to 0. So I have proved the ergodic theorem for these guys here, like in the classical case. The point how to get easily out of this, the LP theorem, it's that you have to know the norm of these operators. This is what I did there. It's clear that the norm for on bounded functions is bounded by 1, and on L1 it's bounded by 1. So I can do interpolation. I know the theorem for a class of functions here. The only thing I have to prove is that this class is dense in LP. And that's, again, doable using DD bar and to prove that if the current of it is extremal, then these guys are dense in LP of whatever, of T wedge omega or another guy. The extremality of the current is certainly crucial at this step. So that's the easy part of the theorem. The other part is to prove a maximal theorem B star UA is lim sup goes to infinity BRU A. And to show an inequality of the following type, MP of B tilde U larger than epsilon is less than C epsilon minus 1 U L1 omega P, MP. Once you have that, the rest is very easy because what you do if you want to prove convergence for V, you just approximate V for U, say, you approximate V by delta V. The theorem is clear for this, and if you take this small enough, you are in business to show that you have convergence. Okay? The delicate point is to prove this estimate, and this I'm not going to do it. It uses heavily the hyperbolic disk and the comparison with the heat kernel for the hyperbolic disk. But it's technical, and I'm going to skip it. Now I realize, oh, maybe, no. Let me just give you a consequence of this, which is may be of interest because, as I told you, I'm mostly interested in the example of Pn with foliations with singular points. And the idea is how much time do you spend near a singularity? And the consequence of this ergodic theorem, or of this convergence of currents, is the following. Is that log plus r over zeta, phi prime zeta, square d lambda zeta is, when there are no singularities, these behave like log 1 over minus 1 minus r, when there are no singularities. And then the theorem says that this is true MP almost everywhere. The theorem says this is true MP almost everywhere. This means that most leaves behave like, with the estimates of the derivative, like when you don't have singularities. Okay, I realized that I didn't discuss one of the main difficulties of this heat equation problem. There is a difficulty here. I have cheated a little bit, but since I have time, I can correct myself. You have this operator STU, which is UTX. So abstractly, as I did it, you prove its ST is a contraction. And that's basically given by the Hill-Yoshida theorem. But you need to know one thing, is that this operator is positive. Somehow you need to prove maximum principle for the heat equation. We are a little bit in trouble because to prove maximum principle for the heat equation, just by contradiction, you take a point where the maximum is reached, and you contradict the usual maximum principle about second derivative. That's it. But here, the solutions are defined only almost everywhere. Hopefully, there is a trick due to Stampacchia to overcome this difficulty that was used for elliptic equations with only measurable coefficients. So it is possible to treat this problem. It's a little technical. I'm not going to give it, but it is possible to treat this problem. So since I have time, I can just erase this. I was thinking, in principle, I have promised in my abstract to discuss entropy, but I better limit myself to what's already on the blackboard. and discuss a little bit this unique ergodicity theorem that is still here. In this context, it is well known that there are no closed currents anyway. So the idea is this: how do you prove uniqueness of the current? And once you have uniqueness of the current, every time you cook up a harmonic current, you know it's that one. Whatever the averaging whatever the averaging you take. Okay? The only point is to check that the limit or the cluster point is DD bar close. So there are two aspects in this. The first one has nothing to do with foliations. And it's valid in compact Kähler manifold, but I'm going just to restrict to P2. You consider currents which satisfy I dd bar t is 0. Then you write this current in sort of canonical form. Since you, for example, consider dt, and this current is of by degree 1, 1. This current is of by degree 2, 1. It is closed because d bar of it is 0 and d of it is 0. So by the dd bar lemma, you can write that d of d bar s. Which means that dt minus d bar s sigma is 0. Okay? Maybe I could have done that. Maybe it's nicer if I do it this way. D bar, D bar. Wait. So this you can write T minus D sigma is omega plus a constant omega. Omega is the Fubini-Studi form, D bar V. You solve the D bar equation in P2. And you end up as a representation of T, using that T is equal to T bar, you end up as a representation of T by C omega plus dV plus D bar V. Not the same V, U. Now, we didn't use at all positivity. And let me assume that T is smooth first. And positive. Then I can consider this guy, it's just a form, a positive form. And from that form, I can compute that it's T omega minus 2 D bar V dV bar. It turns out that this guy is positive. Then I get, as Professor Pereira will say, D bar V, an a priori estimate because this is positive. I get this a priori estimate. Hence, if I take T not smooth, but I regularize by smooth positive, I end up getting that it is always true, even for T non-smooth, that I have this a priori estimate. Then playing with Hodge theory, you get this representation d bar sigma, all these guys are in L2 because I can solve some equation with these guys in L2. Hence, I have a representation of positive harmonic currents by a constant time omega. This sigma, this is in L2, this is in L2, and all the singularities are here. All the singularities are here. Now, this suggests to consider the Dirichlet space of currents, H, current T, not positive or negative, but such that in this representation, d sigma bar is in L2. With a Hilbert space structure, basically, this is the norm. This is the norm. So I have a cohomology theory, meaning I compute modulo I dd bar u. I compute modulo I dd bar u. And since everything is positive, is in L2 here, this integral makes sense. This integral makes sense. I can define a cohomological self-intersection. I don't say that I define this object, but I define this object here. And if I do the computation, maybe there is a 2 here, I don't remember. Which showed that this, if I'm on the hyperplane T omega is 0, this is a hyperplane in this Hilbert space, this intersection is negative definite because this is minus something positive. It's negative definite. So, to prove uniqueness of T, you have just to show that for any T tangent to the foliation, dd bar closed, then integral of T is 0. This is linear algebra because if I have this for everything, then if I have two objects, T minus T and T prime of the same norm, I can consider these guys T minus T prime. But since T plus T prime wedge T plus T prime is 0, all the products are going to be positive, and then I'm going to have this guy, which is not going to be strictly negative. It's going to be 0. contrary to the fact that it should be strictly negative when this is 0. So the strategy of the proof is to show that this guy is 0 for any t laminated. That's the strategy. So the idea is this is difficult to compute. So the idea is to show that t wedge t is limit when epsilon goes to 0, epsilon prime goes to 0, of t epsilon wedge t epsilon prime, where t epsilon and t epsilon prime are approximation of t. But if the now I come back to the foliation. If the approximations are given by foliations, just using the automorphism group of P2, I can give another meaning to this intersection. The other meaning is just the geometric intersection, as you expect. And then it becomes, you have just to compute the geometric intersection of these currents. You have a representation of T epsilon. It is H alpha beta, V alpha, H alpha, V alpha, d mu alpha. And you push that with an automorphism. Okay? And then you have to compute what happens to these functions and to the product of these integrals. Okay? And that's easy when you are away from singularities. The delicate point is that when you are near singularities. But that's just, bookkeeping because the singularities are hyperbolic. You have a precise description of the leaves there. And the important point is to check what is the growth of this harmonic function when you go around of the singularities. You check what is the growth, and then you can compute the product of this integral inside and show it converges to 0. So there is certainly a technical part in the proof, but it's not out of reach. Okay, so I think I'm going to stop here, and that's it.
Questions, remarks? No?
In this decomposition that you wrote for the case of foliation on P2, do we have some simple interpretation for each one of the sums?
No, it is just a canonical, it's a canonical decomposition. Everything is determined uniquely after you use Hodge theory. The point is, when you start with the decomposition just T equals C omega plus dV plus, plus d bar V. Maybe let me write it this way, dV bar. This choice of V is not unique because I can add any d bar S. Okay? It won't change. So I'm just taking the best decomposition. Okay? That means I choose S so that this is as good as possible. and that becomes unique. The point also is somehow that this guy is not unique, but dv bar, no, sorry, I'm just mixing things, but t equals c omega plus ds plus d bar s. S is not unique, but d bar s is unique. And this is what I'm taking advantage of. There is a correspondence here, and it's natural to write it that way. It's sort of Cauchy transform of the current.
Oh, and this is a kind of very naive question. So you made some Birkhoff version for the current on your foliation. Is there some oscillators equivalent? That is, can you make, I don't know, the Lyapunov exponent, the transverse Lyapunov exponent of your foliation for your current?
Yeah, we thought of it actually, and not in this context. I think we have an idea, and it's written in our paper on entropy, because once you define a notion of hyperbolic entropy using distances, as I told you, you can try to measure how leaves get far apart using these distances. And you can define Lyapunov exponents. But to tell you that we know that they are negative or whatever, this I don't know. Just the framework, the idea to introduce several invariants of Lyapunov exponents, or some of them, is there already. It remains certainly to compute in concrete examples. Yes.
I'm not sure I can formulate the question in a good way. In some cases of smooth dynamical systems, you have the stable foliations, which are not foliations because they're only defined almost everywhere.
Yes.
So they are very weak objects.
Yeah.
Very far from this kind of dimension.
Yeah.
Can you do something like hydraulic theory? Can you define harmonic currents for this kind of non-uniformly hyperbolic dynamical systems, leading to laminations which are not laminations?
I believe so, actually. This is, yeah, in some sense. This is related somehow to Nevalina theory and Brody type theorems. So you have a family of objects that are not compact. I answer very vaguely because I don't have a result to tell you to write. And then one instance of that is either you can, at the end, the graphs are going to form a compact family. You can reparameterize to get some compact family, or you get a current. So basically, this is it. Obstruction to compactness is a current. But it's not written formally as this, but the idea is familiar to me in some sense. Yeah?
Maybe a dual question. You told me that maybe there is a notion of transverse Lyapunov exponent.
Yes.
If you are in higher dimension and so on, and if you have you are lucky and you know that you have some negative one, can you have a stable manifold?
I don't have, this year, no, we didn't.
Manifold, stable something.
Yeah, but we didn't develop yet this theory. I can tell you, but somehow way of thinking, our is always Dean, Vietan, and me. Our way of trying to develop the theory, but it's still at a very rudimentary level. The idea is to have a notion of entropy that would be finite even when you have singularities.
Yeah, so I
Okay?
understood why
And
you make that, but
what?
my question was more, like for a measure, you can have its spacing.
Yeah.
Certainly, if your measure have some negative Yarsanov exponent, you would know that there is something converging.
Yeah.
So also for the current, you can have spacing because you have.
Exactly. You have this type of ergodic theorem that gives you a basin for each one, but we are just at the level of Birkhoff theorem, meaning you have many, a priori, infinitely many harmonic measures, okay, and each one has a basin. But we are not yet at the level to say that some basin is what you call physical basin. That we definitely are not yet at that level. The problem is first to define the notions. And that we have progressed because there is a definition of various invariants for the foliation, etc.